So although I've only included a single statement in each of the try blocks that we've used so far, and we can see an example of that on line 43, we've just got the return s.nextInt. You can actually wrap many lines of code in a try, and similarly, the catch block can contain as much code as you need to handle the exception, including attempting to recover from it if that's appropriate for that particular bit of code. But let's take a step back and answer the question, what is an exception? Now, the Java documentation defines an exception as an event which occurs during the execution of a program that disrupts the normal flow of the program's instructions. So I guess that could be summarized more simply as something went wrong somewhere, which is possibly a more useful definition because it leads more naturally to two very important questions. A, what went wrong? And B, what can we do about it? So exception and runtime exception are classes defined in java.lang, and the different types of exceptions that can be called as subclasses of one of these two exceptions. So normally, when catching an exception, you'd specify which subclass of exception to catch. And we saw that earlier with this code on line 43 when we caught the input mismatch exception with the invalid integer. So now we could just catch exception, but it's really a good idea to be more specific and catch a specific exception rather than just generalizing catching, sort of do a catch-all catch, so to speak, with exception. So in other words, we could have changed the code to just be that, and that would work fine, but it's very generic and we're not being specific enough. And it can be useful to actually be specific, and you'll see I'll be talking more about that a little bit later on. So the type of exception thrown answers the question what went wrong. So that's the other reason, one good reason to use that. And you can see on line 45, we know at a glance, oh, okay, there was an input mismatch, and that's because the exception has been named to really make us understand the type of error that's been encountered in the program. So when our code got an input mismatch exception, we can then decide what to do about it. So as it happened, the code didn't do very much. Any invalid input just resulted in 0 being returned. Now this could be a reasonable response in some situations, but in others, the calling method might need to know that there was a problem rather than effectively being told that the user entered the number 0, which is what we did here. So to let the calling method know there was a problem, the code could have thrown the exception. And what that means is passing the exception back to the calling method. So once again, these things are probably best explained with examples. So far we've created a method to perform division and another method to get the number from the user. So by putting them both in the same program, we can look at how exceptions propagate up the call stack. And I'll also explain what that means, what call stack actually means as well. Now we don't need the LBYL code, and we'll start without handling any exceptions just so we can see how Java handles things. The main method is going to call divide, which will call getInt twice to get the two numbers x and y. So this is getting a bit messy. So what I might do is just create another bit of, or another Java class, and we'll do it in there. So we'll put a new one in. We're just going to call this example. And let's just type this in. We need a public static void main, psvm tab. And we want to int result equals divide, which we're going to write that method. And we want to print out the result. Pretty simple, as you can see. And that method is going to be private static int divide. And int x equals getInt, which we're about to write as well. Int y equals getInt. We'll put x is plus x, plus y is plus y. So just dump out the values, and it's going to return x divided by y. And private static int getInt scanner s equals new scanner, and it's going to be system.in as normal to accept input from the keyboard, and we print out a message so the user knows what to do. Please enter an integer, then return this.nextInt. A pretty simple program there. So we'll run it first just to make sure that it works. So we'll do the first one 10, second one 5, 10 divided by 5 is 2, so x is 10, y is 5, so that's obviously working correctly. But also if we run it again, do it the other way around, 5, 10, 5 divided by 10 is 0 again because we're using integer division here. But there are two exceptions that could happen in this program, so just to demonstrate that, firstly, if we just try and divide by 0, so first one 10, the second one 0, now notice the error there is arithmetic exception, divide by 0 over here. Now if we run that again though, and instead of a number put something else, we get a different exception. We get an input mismatch exception. So as expected, we got an error because we saw that in the previous video, and Java automatically prints a stack trace, which is showing the call stack. So the call stack is a list of all the methods, all the method calls at any particular point in a program's execution. Now in this case, it's all the method calls at the point where the program crashed. So each thread of execution has its own call stack, and the thread is shown as the first line of the stack trace, and here it's our main thread. So every time a new method is called, so it's actually placed onto the stack, and when a method returns, it's then removed from the stack. So here we can see that the exception happened in line 864 in the throw4 method of java.util.scanner. Throw4 I should say. So we'll have a look at throw4 in a minute, but our code didn't call it, so it doesn't make much sense to us yet. The next item on the stack is scanner.next. We didn't also call that either directly. So in fact, the best approach to make sense of these traces is generally to start at the bottom and then work back up. So our first code, which is on line 11, is the first item that relates to our code. So obviously this is the com.timbachauca.example.main. So line 11 in example is the first item that relates to our code. And line 11 is where the divide method was called, and the trace shows that it happened in example.java. So the next entry is line 16 in example.divide, and that's where getInt was called, and then the next one after that is on line 25 of getInt. So normally we would stop there because all the entries above that are also out of our code in java.util.scanner class. Now we know that our attempt to get an integer from the keyboard failed, and we should do something to prevent that error from crashing the program. But I'll carry on through the stack at the moment though, because it's useful to see just how to trace errors through different classes and packages. So up until this point, IntelliJ has created links to the line numbers where they appear in the code in the editor. So the links appear in blue, as you can see on the screen there, in the stack trace, and you can click them to be taken to that line of code. So we can, for example, just click on this one, and we get taken to that line of code. You can see the cursor's moved. Likewise, we click up here, we get back to line 11. So once the trace leaves our code, there may still be links, but they're in grey. So you can see the first one where it says scanner.java 2076 is in grey rather than the blue. And that's, of course, if you're using this IntelliJ theme. It might be different if you've themed your IntelliJ installation separately. So next we have, looking up the call stack, I've got on line 2076 scanner.java. So we click on the link for that. And I'll just move this over so we can see a little bit more. And IntelliJ has helpfully loaded the source for scanner and has taken us to that line. We could also control click on the call or command click to nextInt on line 25 back in the code to do the same thing. So the scanner's nextInt method has been overloaded, which is why there seems to be two calls in the stack trace. You can see these two calls here, 2076 and 2117. And our call's ultimately then passed on to nextInt with default radius, as you can see there. So if we click on that again, I'm doing a command click. You can do control if you're on Linux or Windows. That takes us to that method, and we get to the overloaded nextInt method. So that entry is a call to next, as you can see. And looking up here, the next call then goes to scanner.java line 1485. So if we wanted to, we could come back here, click on the scanner.java 2117, and notice the input mismatch exception that gets thrown there. And then we can come back here if we want to next. There's a throw4 there, and that's the code that's been executed here. So we can click on that. Then on line 864, following that through, then ultimately the input mismatch exception on line 864 is where it actually throws a new input mismatch exception. So quite often the exception would be thrown from the method that had the problem, but as you can see in the scanner class, the scanner class uses the throw for method to throw either our mismatch exception or a no such element exception. So that's back here again. As you can see here, so depending on what the problem was, it's throwing one of two different exceptions. So I'm going to be talking more about throwing exceptions later, but for now I'm going to concentrate on what happens when one's thrown and how to handle them. So I said that exceptions are subclasses of the exception class, and exception itself actually extends throwable. So we'll trace the classes back in a minute to see this, but at this point you just really need to know that the throwable constructor fills in the stack trace for the exception. So line 864 that you can see on the screen now for scanner.java creates a new input mismatch exception object that contains the current stack trace. So when the exception itself is thrown, the Java runtime then looks to see what can handle it. So it does that by working back up the call stack. Each method on the stack gets the exception, and if it doesn't handle it, then the exception gets passed on to the previous method on the stack, and so on. So the exception is said to propagate up the call stack, and it keeps getting passed to the calling methods until there's one that actually can handle that exception. So looking at the way the stack trace is printed, it might actually make more sense to talk about propagating down the call stack, but stacks tend to be implemented growing downwards, so we talk about going back up the stack. But eventually, if nothing handles the exception, then the main Java entry point just prints the stack trace and the Java runtime terminates, and that's what actually happened here to the right-hand side of the screen. So in a minute, we're going to modify the program to catch the exception, but first let's continue backtracking to see the exception class hierarchy. So from line 864 of the scanner class, we're going to click on input mismatch exception. So I'm doing command click, but do control click if necessary. Click on that. And you see we're now in the input mismatch exception constructor. And as classes go here, you can see it's pretty basic. There's two constructors and each one just delegates immediately to the super. But if we control click on super, and we get to the base class no such element exception, it's just a sparse. And in fact, exception objects are generally like this. The subclasses exist to provide more granularity so that code can check for different types of errors by catching the subclasses. So we saw no such element exception before. It's the other exception that the throw for method could throw. So input mismatch exception extends no such element exception and exists purely to allow the exception handler to differentiate between the scanner running out of input and the input being invalid. So we can cause a no such element exception in our program, but this video is getting a little bit long, so we'll start looking at doing that in the next video.